Okay, in this video we are going to look at reactions that involve carboxylic acids. The first couple of reactions are going to be synthesis, and actually those are review reactions, and then two new reactions using carboxylic acids. One of them is going to be this reaction that I show here, which is decarboxylation. This is, if you can tell, this is a marijuana plant. And before you get the active ingredient THC, the plant actually has THCA, A for acid. Here's your carboxyl group, and if you heat up the sample, you could do a decarboxylation and release carbon dioxide. Basically, you are removing this carboxyl group and making sure that this carbon gets a hydrogen right there. Therefore, that carbon is now neutral. And the mechanism of this is pretty interesting. Hopefully I'll have time to show you that. But the first thing I want to look at is how to make carboxylic acids using reactions that we've seen before. This is review. And let's give ourselves a couple starting materials. Let's give ourselves a alcohol and skip a couple lines, and we'll also use a alkyl halide. We have a C3 here and a C3 there. The first way to make a carboxylic acid is fairly easy. It's oxidation. You could use potassium dichromate, K2Cr2O7, with sulfuric acid to do a Jones oxidation, and that will oxidize all the way up to the carboxylic acid. You bypass the aldehyde, and you oxidize to the carboxylic acid. This carboxylic acid has 3 carbons also. The other way to make a carboxylic acid we talked about recently in the previous unit, Unit 4, and that's by Grignard reaction or organometallic. The first thing I'm going to do is I'm going to make this into a Grignard reagent and then react it with carbon dioxide. What's the difference between the product that I made in the second synthesis versus the first synthesis? They are both carboxylic acids, but you notice here you have 4 carbons. Okay. So you got to be aware of that you actually add a carbon if you do the addition of carbon dioxide. Those are the two main ways that you're expected to know how to make a carboxylic acid, and I think that's it. There may be, well, there are definitely other ways to make a carboxylic acid, but these are the two main ways. Let us go to a new reaction reduction. Well, here we have oxidation. The backwards of this would be reduction. This is oxidation. The backwards would be reduction. And this is our first new reaction in Unit 5. We'll call this reaction, actually now I'm going to start, I should have done this at the start. I'm going to put the unit number and the reaction letter. This is the first reaction. This is going to be reaction 5A. Reduction. We're able to get a alcohol from an aldehyde and ketone, but what about a carboxylic acid? We need a strong reducing agent, and the reducing agent of choice is going to be lithium aluminum hydride. You want to do this in separate reactions. First LiAlH4, followed by either water or acid. People just use water. Locate the carbon of the carboxyl group and attach a hydroxyl group, and you're done. You go to a primary alcohol. I normally don't teach the mechanism, so I'm not going to teach the mechanism on the video. The thing that I do want people to understand is that this is, I think, the first evidence or first example where there's a difference between LiAlH4 and another hydride reagent, NABH4. I usually use acid as a second step with sodium borohydride. It doesn't matter, you could use H2O, and actually you could have water with sodium borohydride and the reaction will still go. For lithium aluminum hydride, you really got to separate the water and the reagent. Nothing happens here, no reaction. So if you have a carboxylic acid and a maybe ketone in the same molecule, you can selectively reduce that. Let me give you an example, actually. And this molecule is going to have several reducible functional groups. Let us use the strong reducing agent, lithium aluminum hydride, and we'll put a product there. Let us use a less aggressive reducing agent, and I'll show you how I would write it. NABH4, methanol, that should suffice. What other reducing agents do we know? We know this one, H2 with maybe platinum. Oh, yeah, we actually know two more. I'm gonna run out of room. And the one that we most recently looked at was a Clemmensen reduction or a Wolff-Kishner. I am partial actually to Wolff-Kishner. And there's actually one more. Do you remember what that one was? That one was a hydrogenation with rhodium on carbon. If you want, you can go ahead and pause the video and test yourself. Okay. Lithium aluminum hydride can reduce aldehydes, ketones, and carboxylic acid. Not carbon-carbon double bonds. Make sure you have the right number of carbons. Looks like it's 7 there. 1, 2, 3, 4, 5, 6, 7. Sodium borohydride is not strong enough to reduce the carboxyl group, but you do know it will reduce the carbonyl, not the carboxyl. H2PT can reduce aldehydes and ketones and carbon-carbon double bonds, not carboxyl groups. Thus far, you see that it's very hard to reduce a carboxyl group. You have to use, lithium aluminum hydride, but I messed up here. Ketone to alcohol, and also alkene to alkane, but not anything with the carboxyl group. So far, all three of these are different. Just depends which one you want to reduce. You could pick and choose. This Wolff-Kishner, okay, does not work on carboxylic acids. But remember this one, you just totally remove the oxygen. Or you could say you replace a carbonyl group with a CH2. And the last one is it's unusual. You get to reduce the carbon-carbon double bond, but nothing else. I don't expect my students to know any of these mechanisms. I just want them to know how to apply this in the synthesis. Look at these products, they're all different. Okay? They're all different. These are selective reductions. Okay, last or next thing. I am moving kind of fast, but that's fine. Decarboxylation. Decarboxylation. Let me just double check that I'm not missing anything. Okay, good. Decarboxylation, the marijuana reaction. For decarboxylation, you need a special set of circumstances in the molecule. You need what's called a beta-ketoacid. I'll write all that down in just a bit. Reaction 5B, decarboxylation of a beta-ketoacid. We're going to have a carboxylic acid part, and the keto really is a name for a carbonyl. Therefore, there's going to be a carbonyl group, beta, relative to the carboxylic acid. Let me show you that. Start with a carboxyl group, and we're going to call the carbon next to it alpha, and the carbon next to that beta. You have to have a C double bond oxygen that's beta to the carboxyl group, and just by adding heat, something unusual happens. This is a little bit tricky. Take your thumb and let me double check this. Take your thumb and get rid of the carboxyl. Okay, let's trust that. You're going to take your thumb, cover up the carboxyl group, and that's what you're going to draw. Oh, that was confusing. That one. You keep the alpha carbon. You keep the alpha carbon. It actually balances perfectly. Plus CO2. Decarboxylation. Remove carbon dioxide. Does it really balance that well? Everything's the same up to the beta carbon. Then alpha, this has 2 hydrogens. This carbon has now 3 hydrogens. But where did that hydrogen come from? Technically, it didn't come from here, but you could imagine that, oh, yeah, everything's balanced. Every atom that I see here, because that H, you can think of it as now being over here to make a CH3. And we have carbon dioxide. What is carbon dioxide? Carbon dioxide is right here. The CO2, and again, that H gets transferred. When you think about a decarboxylation, you're just going to remove one carbon. Okay, don't remove that alpha carbon. You can even mark it if you want as a reminder that alpha carbon's there. This will also work, don't worry, I'll show you the mechanism because it's pretty neat. This also works with a diacid. Look at this. It's symmetrical. So it doesn't matter which carboxyl group you remove. But once you remove one carboxyl group, in this example, the other carboxyl group cannot be removed. Okay, take your thumb again, or you could use this dotted line idea. We're going to make this the carboxyl group that we're going to remove. You see how still in the beta position that we have a carbon-oxygen double bond. So whether it's an aldehyde or ketone or carboxylic acid, as long as you have that carbon-oxygen double bond, this can be decarboxylated. It can fly off. You don't have to normally draw it in its most preferred conformation. I just typically do this. I just copy everything, copy everything except the carboxyl group. And again, rest assured, you have the right number of hydrogens because this one has one hydrogen, and then by removing this, you do get a second hydrogen, and now that carbon is neutral, plus CO2. You see, now, there could be a way to remove this carboxyl group if somewhere else on the molecule there was a beta-keto group. Okay? Let me do that example. And then the mechanism. If you have a chance to remove multiple carboxyl groups, go for it. And let me make this tert-butyl just to keep track of it. Heat. You can think of this stepwise, and that's what I would suggest. We have two carboxyl groups. Let's remove the one on the right now, like we did before, and we get that, right? You keep the alpha carbon. Let me write that out, actually, alpha carbon. But, you know, what's different between the molecule at the bottom and the molecule above it is that in the beta position, we have another carbonyl group, or a keto group. So the first decarboxylation, I'll get rid of this. If your classmate removes the one on the left, the result is actually the same molecule. But then, the second decarboxylation can occur because of that beta-keto group. And we can do it stepwise. Okay, we'll have this in brackets as parentheses. Let's do this stepwise. Let's take a carboxyl group off one at a time. You see the difference between this intermediate and the product up here? They're almost identical. One big difference is that, oh, I have this in the beta position. Go ahead and put back your Greek letters, beta. Now it's beta to this carboxyl group, so this carboxyl group is now going to come off. You're keeping the alpha carbon. You're keeping the alpha carbon, and I'm going to draw it the way that it looks like on paper. You can make it look fancy, rotate it if you want. But again, you're keeping the alpha carbon. Alright, so if you have a chance to remove multiple carboxyl groups, go ahead and do it, but it has to make sense. It makes sense when a carbon-oxygen double bond is beta to the carboxyl group that you are proposing to remove. Let us take a look at the first example and the mechanism. The first example is drawn like this. But to do the mechanism properly, you may want to redraw this. And let me show you how to redraw it. No reaction, just the molecule twisting and rotating its bonds. And rotating its bonds to look like this. Can you understand that these two are the same molecule? I rotated along this bond right here, and I drew out the oxygen-hydrogen bond. Verify first that this is a beta-ketoacid, beta-ketoacid. Okay, and now we get an idea of why it's important that the keto group be on the beta position. If it was on the gamma, it would be too far away to make this. If it was on the alpha, it would be too cramped to make this. This is a six-membered, how should we say this? Normally the textbook would say this is a six-membered transition state, or you're going to form a six-member transition state. I'm not going to draw the transition state. Well, this is what I'll do. I'll finish up the mechanism and I'll explain why this works. Okay. happens next? Let's do this bond right here. This bond comes down to make a double bond, and this bond goes to the left. Alright, so we're shifting electrons, it looks like, around the, I was going to say ring, but around this molecule here. Alright, for most of you, you haven't seen this example before. You haven't seen a decarboxylation. But based on my mechanism arrows, can you draw me the result? Okay, pause the video, draw the result of my mechanism arrows. I can warn you now that you're not getting the product that we expect. Not yet, at least. Okay, we have this oxygen, which picked up the hydrogen. Okay, that's not what I am expecting, right? I expected a keto. Don't worry about it. Follow the arrows. This second arrow, or this arrow down here, is forming a double bond. What? Okay, so that's weird. But look at this arrow on the right. That's what we expect. Double bond to carbon, and then another double bond to oxygen. Don't put in that bend, because carbon dioxide is linear. So when this happens, yes, it will get out of 120 degrees and make it 180 degrees automatically. Whoa, so this is not a product. I thought we were expecting this up here, right? Same exact starter material. What happened here? I'll give you a clue. This is called an enol. And what do you know enols to do? They form the more stable keto group. Now, I'm not going to show you the mechanism for the tautomerization. Right now, what's more important is that you understand, oh, if I have a beta-ketoacid, then we draw it and have this kind of cyclizing of the electrons to transfer the electrons to get the enol. And do you remember how to draw the keto group? Or the keto form? You just move the double bond to the oxygen and get rid of that hydrogen. I did talk about the mechanism previously, maybe in Organic Chemistry 1. Right? We looked at enol-keto tautomerization first in Organic Chemistry 1. That's your final product, okay, the ketone. Now, think about your thumb trick. If you're doing a decarboxylation, oh, by the way, maybe we should put heat here. Okay, you do have to heat it. But the thumb trick is you take your thumb, get rid of the carboxyl group, okay? Go to the alpha carbon. That is your product of decarboxylation. Okay, look at that. Look what we get when we do the mechanism. Now, even more interesting is the fact that marijuana does not have a beta-keto group. Why does it decarboxylate? You notice here, there's alpha and there's beta. That's not a keto group, that's a hydroxyl group. So why is this decarboxylating? Let me show you the trick that molecule does. I'll do it here actually. THCA. Oops. THCA, I'm not going to draw the whole molecule. I'm just going to draw the part that undergoes the decarboxylation. THCA, centered. THCA, the main part of the molecule looks like this. The part that decarboxylates. Why does this decarboxylate? Because if I cover up most of the molecule, what does that look like to you? That looks like an enol. So here we're going to go to the keto group. Now, benzene ring normally doesn't like to do that. Normally it wants to keep those 3 double bonds around the ring. But a very small percentage, super small actually, equilibrium, okay, a small percentage will turn into this, a keto version of phenol. Keto, enol, or in this case, enol, running out of time, enol and keto. That small percentage that does this, look what we made, alpha, beta, alpha, beta. Now we could do the decarboxylation. But when we do the decarboxylation, okay, I'm not going to draw the mechanism again, but remember the intermediate you get. You get this. Oh, this is perfect actually. See, normally you would convert the enol version of the molecule into keto. But in the case of THC, you're going to keep it like this. And we got rid of CO2. You're going to keep it like this. So when we take a look at that picture, see, you still have essentially a phenol molecule right here, phenol. Okay, we're not going to convert it into the keto because actually the phenol is more stable. That's not going to sink us because, again, even though this is more stable, when this goes to the small percentage of keto, it will automatically or very quickly decarboxylate, and we keep it at the enol form. So that's the side story for THC. Let me show you in the last 1 or 2 minutes, though, this idea that why does it have to be beta? Why can it be alpha or gamma? Because when we draw that draw that conformation right there, and we draw our arrows, and again, this is alpha and this is beta, relative to the carboxyl group that we're removing. Well, yeah, your product is this. This is nothing new. You saw this on the previous page. Okay, that's it. Plus CO2. Again, you keep the alpha carbon, or what was the alpha carbon. What is a transition state? Transition state, typically they mark it as TS with a double dagger. Transition state is the picture of the molecule in between two stable states. So here we have the starting material, here we have the intermediate, but there's a transition state. Okay, it's on top of the hill. So here's your starting material, and I'm going to put the enol a little bit higher because then it's going to go to the keto group. But what I'm interested in is, what is this? What does that look like? So here's the trick. In the process, that bond between carbon, beta, and oxygen is double bond turned to single bond. So halfway, it was 1.5. Okay. Again, this is not hybrid structure, because I know we used dotted lines before, but it is saying that you have 1.5 bonds, just like with a resonance hybrid at times. O to H has no bonds, and over here it has 1 bond. The average of 0 and 1 is a half. So let me finish the rest of this. Make a double bond here. This double bond has always been there, nothing changes. A carbon, and there. And what happened here? We have a single bond, go to the double bond, and we have this. And we have a single bond going to no bond. So I gotta get rid of this actually. We have a half bond here. Because you're making a 6-member transition state, that's actually very stable. And yeah, as the molecule is tumbling and rotating, you will get this 6-member transition state. If the keto group was in a different position, then the bond angles and the stabilization is not going to be quite right. You're not going to be able to get this hydrogen perfectly in place to have this cascade of mechanism errors happen. So maybe that's the main point. By making a six-membered state, transition state, right, you can get that hydrogen in the perfect position to be grabbed by this pi bond. Now, if that carbonyl group was over here, yeah, it may be close, but it's not as close as this, and it doesn't have the perfect geometry. And that's the beauty of six-member transition states, and we'll see that most likely again later, that yes, this conformation is accessible, and it will encourage the movement of these electrons. Decarboxylation and transition state.